Welcome to the ML Ops Production and Engineering in New York City. My name is Nadia, and I'm a senior machine learning engineer at NILAS. Today, I'm honored to be here and have the opportunity to introduce one of our amazing speakers. Before starting, I would like to remind you that you can visit our sponsor booth for a chance to win a $100 Amazon gift card or $200 Starbucks gift card. So just click on the Expo tab and choose a sponsor. Let's start now. The last thing I would like to remind you is that if you have a question, please post it in the chat. I will collect all the questions and ask them directly to our speaker after the presentation. And our speaker of today is Jungo Kasai. Jungo Kasai is a third-year Ph.D. student at the Paul G. Allen School of Computer Science and Engineering at the University of Washington, Seattle, advised by Noah A. Smith. He works on natural language processing and machine learning. His papers have been accepted to conferences such as ACL, ICML, NAACL, and ICLR. His research interests include machine translation, language generation, multilingual natural language processing, and structure prediction. Please join me in welcoming Jungo Kasai.
All right. Now you guys can hear me okay, right? Okay.
Yes.
All right, let's get started. All right, so I'm Jungo from the University of Washington. So I'm presenting fine-tuning pre-trained transformers into RNNs, recurrent networks. This is joint work with a lot of people, as you can see here, from the University of Washington, Microsoft AI2, and Google DeepMind. And this work was mainly done during my internship at Microsoft. All right, so just give you a quick summary of my work. Transformer models outperform RNNs in a wide range of natural language tasks. In particular, we focus on language generation tasks in this talk. But transformer generation costs time complexity quadratic in sequence lengths, and it costs linear space complexity in sentence lengths. So this contrasts with RNNs that generate sentences with linear time and constant space complexity. So to address this bottleneck of transformer generation models, we propose T2R, which fine-tunes pre-trained transformers into RNNs for fast and light memory generation, which is hopefully going to be used in production as well. So we demonstrate that T2R retains accuracy in language modeling and machine translation while speeding up inference generation significantly. Moreover, the T2R conversion takes much less GPU time than, meaning that conversion helps us avoid repeating the expensive process of pre-training of large transformers. So there are many pre-trained transformers out there, and we can just download them and fine-tune them into fast, efficient RNNs in a computationally cheap way, and we can just deploy them in whatever applications we're interested in. Right, so first background and introduction. So the transformer architecture was first proposed in Vaswani and others in 2017. It makes crucial use of parallel training over sequential input on modern GPUs. On the other hand, RNNs, or recurrent neural networks, such as LSTMs and GRUs, can only be trained sequentially, and the opportunity to parallelize training is very limited. So large-scale transformers benefiting from its parallel training outperform RNNs in many tasks, and now there are standard architectures in many NLP research and also applications in industry. So the AI community took transformers much further to improve performance. Now we are seeing sort of an exponential growth in transformer size. And of course, this picture is already outdated. The AI community didn't stop here. In particular, now we have the large GPT-3 language model from OpenAI. So it contains 175 billion parameters. And GPT-3 is already used in many industrial applications and more than 300 apps, like email or writing assistance apps or entertainment-related apps, are using their API. And approximately, GPT-3 generates 4.5 billion words every day. And of course, large-scale transformers are widely used in other important language generation applications than language modeling, such as machine translation. So Google Translate now mainly uses the transformer architecture and generates more than 100 billion words every day. So large-scale transformers have proven useful beyond natural language generation as well. DAL-E is one such example where a transformer model is used to generate images pixel by pixel given a natural language caption. So this is another example where transformers are successful in tasks other than natural language tasks. So yes, we are making substantial progress in language generation, but just like any other problem in life, there's no free lunch. These huge transformers come with significant generation cost. When we generate a sentence of words, transformers needs to compute sequentially, like this GIF. So during training, the architecture makes it possible to parallelize across input positions. But then in generation like this, like in this GIF, the model has to wait until all previous words are generated. So that means that we cannot parallelize generation as opposed to training, and we have to make generation steps sequentially. So this problem of limited parallelization gets severe because each generation step in transformers is computationally expensive. So in particular, it costs quadratic time complexity and linear space or memory complexity, as opposed to RNNs that have linear time and constant memory complexity. So to see the difference between transformers and RNNs, let's look at this simple language generation example. A transformer first generates the, then generate dog. Notice that in order to generate dog, the transformer needs to look at the previous state as well as the current state. So we next generate once, but again, we have to look at all previous states. So because of this property, the computation in the transformers grows linearly in sequence length. And therefore, computational time complexity in total grows quadratically in sequence length. And the memory consumption grows linearly. So now let's turn to RNN generation. It first generates the, just like the transformer. However, when we generate dog, RNN generation departs from the transformer. It only needs to look at the current state. And this means that regardless of how many words we have generated so far, there's only one state that we need to do computation on. Still one state. So the total computation in RNN generation only costs linear complexity in sequence length. And since we only need to store the current state, we can just forget the previous states. The memory consumption is constant regardless of the generated words. So okay, we just saw the computation and memory bottleneck of the transformer architecture. But well, like I said, transformers are deployed successfully in many industrial applications, like GPT-3. However, as we make more progress, this property becomes a bottleneck. We are mostly limited to sentence-level machine translation now, where a model translates text sentence by sentence. But document-level translation is one of the important future goals. When we translate Harry Potter by an AI model to many different languages, for example, we hope that we can keep the translation consistent across the book, not just within each sentence. So this means that translation generation length becomes much longer than most of the current applications of transformer models like GPT-3, like the standard email assistant apps and so on. So generation must be much faster and much more efficient if we want to apply transformers to long text or large image generation. Simultaneous translation is another example where generation speed is critical. We want to make an AI model much faster to use it for international conferences and so on, so that we can laugh at the same joke at the same time and so on. So these are more or less future applications because we have yet to see very successful transform models in such tasks. And addressing the bottleneck of the transformer generation is necessary to get to a next stage. So for this reason, recent work proposed alternative architectures with linear time complexity for sequence length. So these models, unfortunately, often underperform transformers and can be difficult to train due to training instability. Because we have to train these models from scratch, we have to redo the pre-training step. So we change the architecture, we have to train them from scratch. And the training can be more unstable compared to transformers. So our goal is to achieve the speed and efficiency of RNNs while retaining high quality generation of large transformers. So to do so, we propose T2R, which fine-tunes already pre-trained transformers into efficient RNN variants. So now we present our method. So in summary, TTR proceeds with the following 3 steps. First, take an off-the-shelf pre-trained transformer like GPT-3. Then we modified its computation to get an RNN counterpart. Lastly, we fine-tune it with the same language modeling pre-training objective. So let's discuss in more detail. So firstly, transformers consist of several components. The bottleneck that implies quadratic time complexity and linear space complexity is the multi-head attention module. So we focus on this module and leave the other parts as they are. Multi-head attention takes as input key, value, and query vectors. In machine translation cases, keys and values come from the encoder. We have the encoder to decoder model, and which is also called the source, and the queries come from the decoder, which is from the target. Assume that we have n vectors from the source and a current vector on the target side. We first do feature mapping, where we map the source vectors to keys and values and the current target vector to a query. These are standard affine or linear or affine transformations with learnable parameters. So this is sort of a simple, kind of like the simple linear regression model. Then we get a linear combination of these value vectors, v vectors, weighted by the similarities between the query and the keys. So the similarity function is the dot-them exponential function. So we run this procedure multiple times in parallel and concatenate the vectors to get the final output vector in multi-head attention. So that's why it's called multi-head. We do this in parallel multiple times and concatenate them together. So as the generation sequence length grows, the attention computation becomes the bottleneck. It implies quadratic time complexity and linear space complexity in sequence length. So to address this issue, we change the similarity function, the dot-then exponential function, to a 5-feature mapping followed by the dot product. The 5 function is a 1-layer multi-layer perceptron, which is just a feed-forward network, with the ReLU activation that maps query and value vectors to k-dimensional feature space. K here denotes the dimensions of the new feature map, right? The ReLU activation ensures that the similarity, ReLU is just taking the max between 0, 0 and the value, so which means that that's non-negative. So we found that this non-negative similarities make training stable. So once we change the similarity function, we reorder the attention computation by the associativity of matrix multiplication. So now we multiply 5 keys and values first, and then multiply it by 5 cubes. So we are just changing the order of matrix multiplication of the original transformer. So this means that we can translate the attention computation to RNN. In particular, define RNN states, Si and Zi, at each position. Then we can compute those states sequentially. And the output can be computed by multiplying them by 5 of the current query. So because we change the order of the matrix multiplication, we can just store everything into this Si and Zi, and we just forget Si minus 1, S0 up to Si minus 1, S minus 1, and Z0 up to Zi minus 1. So now we further speed up inference generation by collapsing the 5-feature mapping. We speed up the feature mapping as well. Since phi is a single-layer, multi-layer perceptron feed-forward network, we can combine it with the original feature map that produces, remember, that produces the queries and keys by simple matrix multiplication like this. We only need to do this once before inference, and this way we can avoid computing the intermediate queries and key vectors, and we can just simply speed up generation further. So in summary, here's a quick overview of the TTR generation steps, as opposed to the transformers. So we first compute the phi of keys, values, and 5 queries. Then we compute the RNN state and multiply it by 5 queries to get the final representation. So this only costs linear time complexity and constant memory complexity in sequence length. Sequence length here is n. And because k is fixed, this complexity does not grow as the sequence length grows. Right? So again, k here denotes the output feature size of the phi function we are using. So this contrasts with transformers' quadratic time and linear space complexity. So the conversion process. start with a T2R model with all parameters initialized with the pre-trained transformer like GPT-3. Then the 5 MLP parameters we just introduced are all randomly initialized. We then fine-tune the model with the task objective. Notice that we do not approximate the original transformer here. Right? We're not approximating the original GPT-3 or anything. The only fine-tuning objective is the task itself. And because of that, we do not need to generate new training data. So the 5 feature size K we use is much smaller than generation sequence lengths. So in language modeling cases we are experimenting with, we generate 512 consecutive words with K equals 32. So K is much smaller than the sequence length. So the computational saving is very significant. So we just presented our method, but there are many other methods to make transformers efficient. Knowledge distillation is one prominent approach, but notice that knowledge distillation typically generates new training data for smaller models. So we first train a large model and we distill it into a small model. And in this process, we typically generate new training data for the small data or the small model. So, but this generation of new training data can be costly as our pre-trained model becomes larger. If we have a GPT-3, generating new training data using GPT-3 could be very large and very expensive computationally. So there are approaches that compress attention context or sparsify attention patterns, and several works propose methods to speed up generation by parallel generation methods or lightweight decoding. But we know that many of these methods have yet to be empirically evaluated in generation tasks, and some of them can be combined with our method, and we sort of leave it for future work. So now we present our experiments in language modeling and machine translation. So for baselines, we consider the previous models that corresponds to different 5 feature mappings. So TTR uses a learnable multi-layer perceptron feature map, MLP feature map, but we use the ELU mapping and random feature approximation from prior work. So these are just prior works that are related to our method. We choose RFA for random initialization. RFA stands for random feature attention that approximates the transformer attention by random features. And we consistently observed training divergence from the other method called performer from DeepMind. So we don't experiment with this. So for each of these configurations, we experiment with 2 settings: random initialization and fine-tuning from a pre-trained transformer. So here are results from the standard language modeling benchmark, Wikitext 103. It consists of 103 million words sampled from the English Wikipedia, standard language modeling benchmark. Here we measure perplexity by generating 56 words, given previous 256 words. So this is perplexity, so the smaller the better. So we see that RFA from prior work outperforms ELU in this random initialization setting. And K is the 5 feature map size. Since ELU function does not change the input dimensionality, K is fixed to be 128 for ELU, which is the same as head dimensions, the input to the multi-head attention module. Right? Our T2R model outperforms RFA in the random initialization setting. Now we see results from the fine-tuning setting. So we just did a random initialization, but here we do this pre-training. So we fine-tune the model into these RNN variants. T2R benefits from pre-training, leading to a more than 1 perplexity point decrease, but the ELU and RFA baselines do not improve as much. So as a result, our T2R outperforms them by 2 perplexity points. But when compared to the original pre-trained transformer, T2R with pre-training is still 1 perplexity point worse. Nonetheless, the perplexity gap can be closed by T2R 75%, where every 4th layer from the top is kept as the original transformer layer, and the model is fine-tuned in the same way as T2R. This suggests that keeping a small fraction of the expensive quadratic attention layers can provide an effective middle ground between efficiency and accuracy of language generation. Now we look at GPU hours necessary until convergence in these configurations is achieved. So we see that fine-tuning settings is about 5 times faster, which is measured in GPU hours, than training a model from scratch. So these results illustrate that a lightweight model can be obtained without repeating the expensive training of large-scale pre-trained language models, again, like GPT-3 or BERT. So here are machine translation results from so these are machine translation results from standard WMT WMT English German and English French datasets. K here indicates again 5 feature sizes. We have 2 of them because we have 2 types of multi-head attention in machine translation models as opposed to language models. So unlike the language modeling experiments, in the random setting, T2R underperforms the 2 baselines. However, when pre-training and fine-tuning are done, T2R improves most, and it outperforms the 2 baselines. So now in the machine translation case, T2R with pre-training and fine-tuning yields pretty much the same blue score as the original transformer model. So here we are able to retain the same accuracy of the original transformer machine translation model in this efficient alternative. So we present generation speed results here with varying sequence lengths. Here we take the previous machine translation models and assume that the source and target have the same lengths. First, we see that T2R model achieves constant decoded tokens per second, which is because of its linear time complexity. On the other hand, the transformers generate tokens per second decrease as the sequence gets longer because of the quadratic time complexity. It has to look at all the previous states that it has generated so far. So comparing T2R and the ELU baselines, we see a consistent 50% speed up across varying sequence lengths. And this comes from the smaller feature sizes, smaller Ks we use in our T2R model. And comparing T2R and RFA, random feature attention, even though the feature size is the same, we still see a 15% speed up because T2R feature map skips the intermediate step of generating intermediate queries. So RFA needs the intermediate step of generating these vectors because it normalizes, it changes the scale of the vectors to control the approximation error compared to the transform model. We don't have to do this in our T2R model. So here are the memory consumptions from the various models' attention module. So we see that T2R only costs constant memory regardless of the sequence lengths, as opposed to the linear memory footprints of the transformer. So however many tokens we have, however many words we have to generate, our memory consumption is pretty much fixed in this model. So this plot presents validation perplexity. So again, the smaller the better of T2R models with varying feature sizes. We see that the trade-off between efficiency and accuracy here, as the perplexity goes down, as the feature size K goes up. But we see that the pre-training setting, so the pre-training is changing the curve, pushing the curve down, so that this means that pre-training is leading to a Pareto improvement in this trade-off compared to random initialization. Compare the resulting the attention weight distribution to the original transform model in language modeling. So this is comparing the coefficients of the weighted sums in the attention modules between different models. So we see that the T2R fine-tuning process is decreasing the Euclidean distance. So the y-axis denotes some sort of distance between the original transformers attention distribution and the new attention distribution from the original so it's decreasing the distance from the original transformer attention distribution by doing this fine-tuning, right? So this is a bit surprising since, again, the fine-tuning supervision, we fine-tune the model solely with the language modeling objective. So the language modeling objective is just predicting the next word given the previous words. So there's no transformer, there's no direct supervision that tells you that we have to make the attention distribution similar to the original transformer, but some sort of implicit approximation is happening here. So conclusion in future work, our T2R methods convert a pre-trained transformer to an RNN counterpart that reduces the time and memory cost of autoregressive language generation. T2R improves the trade-off between efficiency and accuracy over random initialization and the linear time complexity baselines from prior work. So this result provides further support for the claim that large-scale pre-trained models can be compressed into lightweight inference models while retaining high performance. And this is very important because training can be parallelized. So training can be done on huge infrastructure, but then inference it's hard to parallelize. But then if we can have a very good inference model that speeds up generation, we can use these inference models for many applications out there. So in future work, we are interested in exploring methods to speed up the conversion process. So the conversion process took about 1/5 of the time compared to the original pre-training time, but that's still significant. GPT-3 is training very long on many GPUs, so we hope that we can develop a way to further reduce the time necessary for this conversion. So we are also interested in improving the performance with random initialization. Here we do fine tuning, but it would be great if we can improve the performance from random initialization as well, just like the transformers. And then we're also interested in applying a method to more generation tasks, such as summarization, and even to known generation tasks. And this is the end of my talk. And thank you.
Thank you so much, Jungo, for the presentation. Okay, so right now we don't have any question, but please, people, post your question in the chat. Let's wait maybe a couple of minutes. Meanwhile, I can tell you that I think it's really an interesting concept. So a lot of companies, they don't have a resource for training huge models. So being able to go back to a smaller version, it's definitely open up to more usage for those models.
Yeah, I definitely agree with that. And right, our competition. So parallelization is very important. We're getting many GPUs, but there's a heat wall. We can't make the clock time faster, and for inference, we can't use this kind of parallelization. So I think it's very important to make the inference manageable for many applications, and especially given more advanced applications that we are interested in the future, like large document translation, instead of just translating a sentence and so on. We hopefully in the near future, we'll be able to translate large amount of document in a consistent way, or even creating a new novel or AI screenwriter or something like that.
Okay, still no question. So maybe I can ask a question. So it's more like a curiosity. So I know you are really interested in multi-language, natural language processing. So for some people that it's starting now to develop a model in multiple language, what approach do you suggest to start with? Maybe a single model, multi-language, or maybe start
Right.
with multiple model, each of them handling only one language?
Yeah, so it depends on the language. If you have a lot of data for that language, it's safe to assume that you can just train a relatively large model on that language alone. But if your language is relatively for your task, if you don't have much data for that task in that language, I think it's very reasonable to have a large model trained on multiple languages like English and other languages like Spanish or Japanese on. Yeah, so I think another challenge. So this is sort of a data scarcity problem, right? So unfortunately, a lot of benchmarks are limited to English. So if we want to extend our model to different languages, that could be a challenge. Another challenge could be sort of a data asymmetry. So for example, we have lots of question answering, for example, question answering data for English, but then these benchmarks are not really useful for many languages because people typically translate these benchmarks into whatever language they're interested in, but then the question distribution from English speakers and Japanese speakers is typically different. English speakers might ask more about American politics or sports, but the Japanese speakers might have different interests. So I think benchmark is another thing we should work on when we want to develop a multilingual model, which is often ignored in the current academic community. But I think gradually we're getting sort of interest in this kind of direction of diversifying tasks, diversifying benchmarks, as well as not just diversifying models. Yeah.
Yeah, that's an interesting point of view. So I never thought about that. Maybe also the culture affect the type of question that somebody can ask. So based on that, yeah, you should definitely have a different set, not translate a set coming from another culture, but each culture should have like their own set of questions on who to benchmark.
Yep.
That's a good point. Okay, so thank you so much for answering my curiosity. And yeah, I don't see any other question coming. So I think we can close it here. Or if you want to add something else.
Yeah. So my paper is available online. So feel free to read it if you're interested. Yep. And thank you so much for coming.
Yeah, would you mind share again the title of your paper?
Oh yeah, it's the same as my title of the talk. So fine-tuning pre-trained transformers into RNNs. Yeah.
Okay,
Well, yeah. Okay.
perfect. Thank you so much. Thank you so much, everyone, for attending. And thank you so much, Jungo. Very interesting presentation. I really enjoyed it.
Thank you so much.
And thank you so much for participating to MLOps.
Thank you.
Bye.
Bye.